Well, hello everyone. Welcome to Exploiting Interprocess Communication with new desynchronization primitives. My name is Martin Doyhenard. I work at Onapsis as a security researcher. And in Onapsis, we focus in ERP security, in critical business application security. And that is software or systems that are used in different companies, or at least in most companies in the world, to manage their most important assets, like their business processes, such as you can see operations, financials, human capital, anything that is related to the day-by-day work in a company. So they are really critical software. They are probably the most important software in a company. If we can compromise one of these systems, then we are talking about causing important damage in a company, like stopping their entire process. And among the different vendors of ERPs or different systems like related with critical applications, SAP is probably the most popular one and the most used one, with over 400,000 installations in the world. That includes 90% of Fortune 500 companies. And as you can see, there are different modules in SAP and in any ERP in the world that can be used to manage a lot of different things. So different installations. So there are no similar installations in different business. So the only thing that is common in all the SAP systems is that they expose their application through web services. And there is true in any kind of stack, like Java or ABAP or S4HANA, which is or the cloud, the system using the cloud. So they expose all these services through HTTP, and they use a proprietary HTTP server, which is called the Internet Communication Manager, or ICM. Sorry. Okay, so the ICM is the component used to communicate the SAP system with the outside world. That is, with any client being another vendor, being an employee, being, a bank, being other SAP systems. So this is quite an important component for SAP. We don't have the source code, so the only thing we have is this small diagram that SAP provides, which tells us the architecture. But we are going to see how all these components work together. And even though the ICM is expected to work with HTTP and is used to expose these different web services, it can also talk different protocols such as P4, which is a proprietary protocol similar to RMA in Java, IOP, SMTP, many other protocols. But its main purpose, again, is to communicate with HTTP and HTTPS. And the thing that makes really interesting the ICM in SAP is that it's present by default in all SAP installations. So no matter which installation we are seeing, which SAP system, no matter which company we talk about, we are always going to see this component, this ICM present, even in Web Dispatcher, which is a web proxy, in S4HANA, which is the part of the cloud of SAP, or any stack, on-premise, cloud, whatever we want, we are always going to see this small component exposed, which is the HTTP server at the end of the day. So as I said, this is the small diagram that SAP provides to us. It's not really useful. So instead of that, we are going to see an abstraction of this diagram, and we are going to go part by part to understand how this actually works. So let's think of the ICM as an HTTP server. And when the idea of the HTTP server is, of course, communicate with clients, receive requests, and create responses for those requests. So when a client wants to use the ICM, it will first start a TCP connection, okay? And when this happens, the ICM will assign a worker thread, which is just a thread ready to receive and create responses for requests. And so once the TCP connection is created, the client will send a request. The ICM will use the HTTP parser to understand the request, and then it will choose some internal handlers that will try to resolve the request with static functions, okay? Like, for example, using the cache or some static responses that are created for some requests. But in most cases, this won't work. And remember, the ICM is just an HTTP server, so the business logic is not inside the ICM. It's actually in a different process, which is called the worker process. This is, in most cases, Java or Eva process, Java Eva virtual machine. And so the ICM needs to send this request to the worker process so that all the business logic applies there, and a response is generated and forwarded back to the client. So if you see this small diagram, you can see that the ICM is going to communicate with the worker process using something called memory pipes. And what are these memory pipes? So SAP calls them MPI, which is an MPI or a framework that is used to exchange data between both the ICM and the worker process internally. And the idea is, instead of sending the entire request and receiving the entire response from one process to another and copying a lot of data, which is quite inefficient, the ICM will use this MPI handler, which is the API or the framework, to send the requests and responses using the shared memory. Okay, so instead of sending the entire request, it will just send an MPI pointer pointing to the specific position in the shared memory, so that the request can be created and written in memory just once. And these MPI pointers are going to point to MPI buffers, which are fixed size. They are 2 to the 16th. This is 65 kilobytes. And they will be, again, reserved and freed by both the worker thread and the worker process using the MPI handler. So let's see an example of how this works. When a request arrives to the ICM, it will reach the socket, which is the TCP socket created for this connection. It is called the input-output handler in SAP. And when the worker thread is ready to process a new request, it will read from this socket. It will first reserve a new MPI buffer using the MPI handler. And then it will store the request in this position. Okay? So now, when the worker thread first calls the parser, then it calls the internal handlers. If the internal handlers fail to resolve the request, it will have to send it to the Java or Eva process, the worker process. So it will just send the MPI pointer, the reference to this position. The Java or Eva process will generate the response. It will also reserve a new MPI buffer. It will store the response there, send the MPI pointer, and now the worker thread is ready to send and forward the response back to the client. Then the MPI buffers are freed so that other worker threads can use it or other worker process. And the references are cleared from the worker thread. I also talked about internal handlers. So what is an internal handler? Which is actually a function that is inside the binary of the ICM. And when the HTTP parser reads the request, it will decide which of these internal handlers should be included in the list to resolve the request. Now, there is a list of handlers that will be created, and they will be called one by one. And if any of those handlers is able to generate a response, then all the other handlers are removed, and the response is forwarded back to the client. First, we have the cache handler. This is, by default, is always present there, and it will always be called, no matter which is the URL, no matter the method, even if it is a post method, no matter what, the cache handler is always going to be called. And of course, as the name says, it will try to use the internal cache to resolve the request. If there is a response stored for that object, then it will forward it back to the client. Then we have the admin handler and the authentication handler. Both of them are also by default. There is no extra configuration needed. However, they are only going to be called if the URL matches a specific prefix. That is, the admin handler is going to be called if it's the prefix is /SAP/admin. The authentication handler is going to be called if the URL is some prefix that is configured also. Then we have the modification, file access, and redirect handlers. They are not really important for us because they are not by default. You need to set them in a configuration file. And finally, the Java or ABAP handler, which are both always included and at the end of the list, because if no other handler is able to resolve the request, then they will forward the request to the worker process. As you see, each of these handlers is a specific function, so they will be called just to try to resolve the request before sending it to the worker process. Let's see an example of the request being resolved by an internal handler. So again, we see that the client sends a request to /SAP/admin. Again, the worker thread will reserve an MPI buffer. It will store the request there. And now the HTTP parser will decide which handlers should be included. First, we have the cache handler. Then we have the admin handler. The cache handler, as I say, is always called. Then in this case, the admin handler, because the URL starts with /SCP/admin. And then, as always, the Java or ABAP handler, depending on the stack. So when internal handlers are called, they are called in order. First, the cache handler. In this case, let's say it fails to resolve the request, so it's removed. Then we have the admin handler. In this case, we will say that it is able to resolve the request, so it will generate a response. In this case, it will be stored in the heap. That is important later. And the response is going to be forwarded back to the client. All the other handlers removed. And again, the MPI buffer will be freed and the reference lost. So, as I said, MPI buffers are fixed size. This means that they can only store a request smaller than 65 kilobytes of data. But we know that requests can be longer than that. So what if we send a request that is longer, or we will call it a large request, than 65 kilobytes? That is not actually that long, but in this example, we will say that is a long request. So if we send a request with, for example, content length 66,000 bytes, the ICM will first reserve an MPI buffer. It will store the first 65 kilobytes of data, and then it will call the HTTP parser and the internal handlers. And that is because the internal handlers are not supposed to resolve really big requests. They are just going to see the headers, and they're going to try to resolve it using that. So they are not expecting to resolve a big request. If the internal handlers fail to resolve this, which is the expected case, because, as I said, they shouldn't be able to resolve large requests, the rest of the requests will be placed in another MPI buffer. If it's even longer, then more MPI buffers can be used. And then all these MPI pointers are going to be sent to the Java or ABAP process. The worker process will generate a response. It will store it in the MPI, in the jar memory, in the MPI buffer, send the reference back to the ICM, and now the ICM can forward the response back to the client. But in this case, as more than one buffer was used for the request or for the response, the MPI fewer buffers is going to be called, and this will remove all the buffers in just one function. And then, again, all the references will be deleted. Okay, so now I'm going to show you the first vulnerability. This vulnerability is going to look at, it's a really simple vulnerability. However, it can be exploited to completely compromise a system. And we are going to see some ideas combining desynchronization, which is a kind of exploitation in HTTP, with these vulnerabilities, these low-level vulnerabilities. So as I said, what if we send a request that is longer than 65 kilobytes, but in this case, it's resolved by an internal handler? So if we send something to /SAP/admin that we know it's going to be resolved, and the request is large, the first thing is going to happen is the ICM is going to reserve an MPI buffer. It will store the first 65 kilobytes, and then it will call the internal handlers. The cache handler will fail, and now the admin handler will be able to resolve the request. Okay, this can also be done with a cache handler. No matter which handler, if we are able to resolve the request, we allow request with an internal handler, then this is going to happen. The response is going to be forwarded back to the client, and the MPI buffer will be freed. However, as you see, the extra part of the request is still on the socket. So the worker thread thinks that the request response cycle has completed. So now the worker thread will read from the socket and will use the rest of the request as a new request. Okay, so it will use all the body as if it was another isolated request. And if you know something about HTTP smuggling or HTTP desynchronization, then you know this is a vulnerability. And this is because the ICM is splitting a request while other proxies will not. Okay, so first, I expect most of you already know what desynchronization is in HTTP. It has been around for the last 5-6 years. It's one of the hot topics in web security. But I'm going to briefly explain the idea. So whenever we have a proxy and a backend, which is the normal case nowadays, and someone sends, for example, 2 requests, and then another client sends 2 requests connected to the same proxy, the proxy will reuse the same connection with the backend. But if everything works as expected, the first 2 requests will be sent to the backend, and the proxy will know that these are 2 different requests. The backend will see again the same 2 different requests with the same size as the proxy. It will resolve the first one, send it to the attacker, in this case the attacker. The second one will again be sent by the attacker, and then the proxy will forward the next request to the proxy, the backend will resolve it, send it to the client. So this is how it's supposed to work. However, in this case, we have a vulnerability that allows us to send something to the proxy, which the proxy will think is an isolated message. It will like one message. It will send it to the backend, but the backend will split that, and then the rest of the request that is splitted will affect the client. Okay, so let's see an example. We have this request which should affect the ICM because we are sending a request to /SAP/admin. Okay, the request is longer than 65 kilobytes. Okay, and actually the 65 kilobytes stop exactly here before the get in the body. Okay, we have this A to 65,370 is actually a lot of A's. And this is going to cause that the backend splits the connection. They split the request. So when the attacker sends this to the backend, the proxy will forward this as an isolated message, but the backend will split this into 2. Okay, so the first part is in yellow, is all the first requests until they get to smuggled, and this will be resolved by the backend. It will send the response back to the proxy, and the proxy will know that this corresponds to the request that the attacker sent. Okay, but as you can see, we have an extra string there in the backend, which is not even complete because there is no line feed, 2 line feeds at the end, so the headers are not completed. So the backend will wait for more data to complete this request. And when the client sends a new request to the proxy will forward this to the backend, okay, and it will be concatenated with the rest of with what the attacker injected, okay. So the backend will think that this is an entire request, and it will generate a response for this and forward it back to the client. But the client actually sent a request to get some resource, and the request that's going to be processed by the backend is get smuggled. Okay, so we can do anything with this, like for example, creating some request to an XSS, creating some malicious response out of this, and affecting the client. Or we can also use this to cause cross-site request forgery by using the credentials of the client or like the cookies of the client, and do whatever we want using the request concatenated with the client. But in the case of the ICM, we can do some even better things. Okay, first I want to say that what's really important and really interesting about this is that there is no proxy in the world that will think that this request is a malicious request. Okay, because the content length is actually matching the content length is actually matching the entire request, the entire body. Okay, so the entire thing is more than 65 kilobytes, but there is nothing strange with this. Okay, any proxy will say, okay, this is an isolated request, just forward it as one. No problem here. Okay, so to compromise the SAP, we are going to use NWA endpoint. This application is present in all SAPs and is used to redirect the user back to a login URL. And it provides 2 interesting features: an open redirect. This is not actually a vulnerability because we need to inject in the host header. But as you can see, whenever we send a request to NWA and we set something in the host header, then the redirect URL will send us to the host header we send, in this case, attacker.com. Okay? And also, we have a parameter reflection. We can reflect anything we send in the body of the post request back in the query string of the relocation URL. So this is going to be really useful for us to generate an attack. The idea, combining both the NWA endpoint and the vulnerability I just explained, is to send the attacker will send a payload, okay, This payload is just like we saw in the previous example. It's a get to /sap/admin. It's going to be resolved by the admin handler. It's longer than 65 kilobytes, and it will be split right in the post of the body. So when this is sent to the ICM will split them. Will split this request. It will generate a response for the first part. Okay, it will be sent back to the attacker. The response is not important. What is important is that we left something in the ICM, and that is a post to NWA with the host being evil.com. That is something we control as an attacker. And with a content length of 100, but we didn't send anything in the body. So the ICM will wait for more data before it is able to complete this request. So when a victim sends a request through the proxy, this request is going to reach the ICM. Okay, in this case, it's just a regular request, including his cookies. And the ICM will concatenate this with the post that we injected. So it will take the first 100 bytes and it will use it as the body of this request. And now, if you remember, the request that is going to be, the response that is going to be issued is to NWA. It will use the host that we injected is evil.com. So it will redirect anyone to evil.com. And it will reflect these 100 bytes, which actually contain the original request from the victim, in the query string of the redirection. Okay, so this is going to be sent to the victim. It's a redirect to evil.com, and this redirect will contain his original request. So when the victim's browser receives this response, it will send a new request back to evil.com, containing, in this case, the secret cookie of the victim. So we will be able to hijack any victim's request and any victim's cookies just by sending this payload, the payload I already showed. Okay. So what's also interesting about this vulnerability is that, as I said, any proxy will forward this, and this is because we are not using any special HTTP header or anything strange to actually reach this desynchronization. We are just using a specific error in the ICM, an internal error that will not be recognized by anyone. And we can send the same attack just by using a form in an HTML page. Okay, so we can create an HTML with this form saying sending a request to /sap/admin with the padding, which is a lot of A's, and with the injection, which is the post to evil.com with the content length 100, and will be sent automatically. And using this, we can actually create the attack without having to send it through burp or through any kind of script. We just use HTML, and it's really interesting to use this because we can create a botnet out of this attack. So remember, the victim would send his credentials to the evil.com, but what if evil.com then responds with what we already saw with this special form that is going to generate a new attack? Okay, so when the victim receives this malicious form, it will issue a new payload. This new payload will go to the ICM, it will get splitted, and again, the attack will be created by this time by the victim. So we will be able to continue this attack as many times as we want without having to interact with the ICM and just having an evil.com server that will generate the attacks. Okay. Let's see an example out of this. So first, we see how the client or the victim is sending a request. Okay, it's sending a request to start page. Nothing strange here. It's also sending his cookies. Okay. So we see that it's receiving a 200 response that is expected. Now the attacker will send his malicious request, his payload, which is to /sap/admin. It contains a lot of X's, being the padding, and at the end it will contain the injection, which is the post to NWA, and with the host header being malicious domain, which is controlled by the attacker. So when we send this, we will receive the first response, but we had been injecting something, so when the victim sends the same request, instead of receiving the 200, he will receive a 302, which is a redirection. And he will be redirected to malicious domain. And he will be sending, of course, his cookies and his first 200 bytes, in this case, of the request. So when the browser follows the redirection, he will send, as you see, the cookies, or actually the entire request, to malicious domain. And there he will place the cookies and his first 200 bytes of the request. But also, as you can see, the malicious domain responded with the form that I already mentioned. Okay, this form will cause that the browser issues a new request to the SAP system, and it will continue the attack. So we will create a botnet just with one request. Okay. Thank you. Okay, so this vulnerability can be used to compromise the entire system, but still we rely on proxies and some other users sending their requests. So let's see some other features of the ICM to see if we can do something even better. So we are going to see the pipelining feature. Pipelining is just the ability in HTTP to send multiple requests one after the other. Okay, so we can send concatenated requests, and all the proxies and all the backends will know where each request starts and where each request ends. So the idea is that if we send 2 requests concatenated, which is something that is valid, we are not actually causing any desynchronization. We just send 2 requests, as the first example I saw. The ICM will first store the 2 requests in a specific MPI buffer. But when the HTTP parser reads the request, it will recognize the second one, and it will place it in a new MPI buffer. Okay, so now the ICM worker thread will work on the first request. Okay, we'll send the MPI pointer to the Java process. The Java process will generate a response, place it in the MPI buffer, as always, send it back to the worker thread, forward it to the client. Now it will free the MPI buffers, but it will then continue with the second request that is in the MPI buffers. Okay, it will send it to the Java process, it will work it as a new isolated request, and everything will work as expected. Okay, but what if we send 2 requests, 2 pipeline requests, but the first request is a large request, that is more than 65 kilobytes of data? So if that's the case, we are going to see that the worker thread is first, again, going to reserve an MPI buffer. It will place the request there. Then the HTTP parser will recognize that there is an extra request. Sorry, again. The worker thread will place it in the MPI buffer. Then, before sending it to the Java process, it will read the rest of the request. It will place it in a new MPI buffer. But now the HTTP parser will recognize there is an extra request. So it will reserve a new MPI buffer. It will store the second request there. And it will send the first 2 MPI buffers to the Java process because they are related to the first request. This will be resolved. The response is going to be forwarded, but now the MPI free all buffers is going to be called. And the MPI free all buffers will free all the buffers related to this worker thread. And that includes the MPI buffer that was being used by the second request. So right now we will have a reference to an MPI buffer that is actually free. So if you know about these vulnerabilities, this is an MPI. This is a use after free vulnerability. We are going to be able to use something that is going to be free, something that is other worker threads can also reserve and use. Okay. Now, when we free a buffer, we don't lose the reference to that buffer. That is a different function. That's the one calling that is the one removing the references. So we are still able to access this MPI buffer, even though it's free. when the worker thread tries to send this to the Java process, we will see an error because the Java process will see that the MPI buffer is free, so it cannot work with this. So we need to do something else to actually exploit the vulnerability. And the idea is we are going to try to tamper requests from other connections just by using the MPI buffer that is free and that is being used by another worker thread. So in this case, each worker thread we see here is a different connection, is a different TCP connection to the ICM. Okay, so again, let's say that the first worker thread, which is the attacker, sends a large request with a pipeline request. Again, we are going to be able to obtain 2 different buffers just for the first request and an extra one for the pipeline request. Okay, if we send an extra character, it will be recognized as a new request. So just with 1 extra character, we can generate a new MPI buffer. So now the worker thread will send these references to the Java process, the first 2 ones. The worker process will generate a response. It will be forwarded to the client. And again, all the buffers are going to be freed, including the one we have the X, which is the extra character, and we are using for another request. So right now, the worker thread 1, which is the attacker, has a reference for the MPI buffer with just 1 character, and the offset is 1, because when more data arrives to the ICM, then it will be written in the first position, after the first position. Now, when the worker thread tries to resolve the next request, it will see that it's not possible because the request is not completed, as we saw in the previous examples. So it will be set into read mode, and it will wait for more data coming from this connection. But at that moment, we can say that the worker thread 2, which is another client, maybe a victim, sends a request or receives a request from the victim, and so it will try to reserve a new MPI buffer. In this case, it will be reserving the same buffer that we have, or that we are using in worker thread 1 for our pipeline request. This is possible because the way that the MPI handler stores the free MPI buffers is using a stack. So probably the last free buffer is going to be the one that is going to be used in the future, in the next iteration. So again, when the worker thread 2 receives the request, reserves the MPI buffer, and stores the request there, it will tamper what we already placed there, which was an X. And now, if we are able to write something else in the worker thread 1, just at this moment, we are going to be able to tamper the entire request of the victim, because we are writing at offset 1 at this point. So actually, we are going to be able to tamper anything from the first byte. In this case, we can modify the behavior of the request from the victim that will be sent to the Java process. The Java process will generate a response, but this response is related to the thing we tampered, okay, to the new request. So we can do the same as we did with the previous vulnerability. We can modify anything we want and generate a response out of the new request. Okay, this will be sent to the victim, and we will be able to tamper the request. But even though we can tamper and we can modify the request, we will still need to find some response that actually performs something, for example, a cross-site scripting or something like that. But if we don't have that, then we need to create a new response. And we are going to do this by tampering the responses instead of the requests. So as you have saw, the MPI buffers are multi-purpose. This means that you can use the same MPI buffer both for requests and for responses. So what if we have tampered or have hijacked an MPI buffer? That is, we have a reference to a free MPI buffer, but when the worker thread 2 reserves a buffer for the request, instead of using the same one as we did, use another. Okay, this is just timing. We need to send a few requests, and sometimes the worker thread 2 will reserve the same MPI buffer, sometimes another one. So in this case, the worker thread 2 has reserved another MPI buffer, generate a request, and this has been sent to the Java process. When the Java process generates a response, instead of placing it in any buffer, it will place it in the same buffer as that we control from the request of the worker thread 1. So now we have a reference to the response that is that has been generated for worker thread 2. So if at that point we are able to send something in the worker thread 1, we will be able to tamper not the request, but the response of the worker thread 2. So instead of creating something that will be processed as a request, we will be able to modify the entire response and generate any arbitrary response containing, for example, a script or anything we want to modify the behavior of the browser in worker thread 2. But there is something even better that we can do, and that is when the response is sent back to a worker thread, it will actually be parsed again, and some response handlers will be called, which are just the same as the request ones. But in this case, the cache handler is going to be called because we have tampered the response, we created a new response, and we included the SAP's cache control header. The SAP cache control header is a specific header that is written in the binary, that is a hard-coded string, and that is going to be looked to know if the response should be stored in the cache or not. So in this case, we are telling the ICM that this response should be stored in the cache for the resource that the worker thread 2 issued. Okay, so the cache handler will see this. It will say, okay, for the object A, I will store the response that we tampered. Okay, so now anytime someone requests to A, he will receive this response, which is the one that the attacker created. Okay, so we will be able to modify persistently the behavior of the ICM. And we can play the role of worker thread 2. Okay, so we could be the attacker and the victim, so that we can choose which is the endpoint, and we can start poisoning all the endpoints in an application and creating arbitrary responses for each of the endpoints we want. Okay, so this is an example. We see that when we send a request to SAP Java at port 50,000 to start page, we receive the expected response, which is the application start page. Now we are going to use this Python script, which is going to try to poison a specific endpoint. In this case, we are going to, instead of saying A, we are going to say poison the start page. And what the script is going to try to do is, first, it will create connections. That is a connection for worker thread 1 and a connection for worker thread 2. With worker thread 1, it will hijack an MPI buffer. Okay, so we will have a reference to a free buffer. Then it will generate a lot of requests for worker thread 2 to start page. So it will try to cause that desynchronization in which we are able to modify and tamper the response. And it will try, of course, to tamper the response. Then it will try to verify if the response was modified persistently by just requesting to start page and seeing if it was modified. Of course, this will take a few attempts because, as I said, this is not deterministic. We need to actually tamper the response at the specific moment it is being sent to the client. But after a few attempts, we are going to see that this works. Okay, so here it was able to modify the behavior. So the start page was modified permanently in the ICM. So when a client sends a request to start page, instead of receiving the thing it's expected, he will receive an arbitrary response with this alert in JavaScript. Okay, so finally, I'm going to explain how to use this vulnerability to actually perform a heap buffer overflow, and then, of course, try to get remote command execution. So again, we said that we were able to hijack a buffer. The worker thread 2 already issued a request. It was sent to the Java process, and now the Java process is going to generate a response. We haven't tampered anything yet. And let's say that the worker thread 2 generated a request that is going to actually generate a response with this SAP cache control header. So actually, get to B will generate a response with SAP cache control without having to tamper anything, okay? So at that point, the MPI buffer will store the actual response, nothing strange here. It will send it to the worker thread 2, and the worker thread 2 will call the parser and then the handlers. First, the parser, it will send it to the client. We haven't attacked anything yet. Now the cache handler is going to be called, and the cache handler, as I said, is going to store this in the cache, because we saw that it has the SAP cache control header. But what is the cache of the ICM? It's actually a file in the file system, okay? It's called the cache file. And this cache file not only contains the response, but also contains some headers that are going to indicate some important things about the response that is stored. Okay, in this case, it's storing the length of the entire response. It's storing the body, the length of the body. It's storing if it's encoded, and some other information. Okay? And then it's going to store the response. But if we are able to modify or tamper the response at that specific moment, what is going to happen, and we can tamper it using creating a longer or shorter response, what is going to happen is that the response being stored in this cache file will not match the headers stored here. Okay, so the length of the entire request in this cache file states that is 95. However, we said in the response something is 106. So this response is longer than what is stated in the headers of the cache file. So this is a corrupt file, meaning that when we try to access this, okay, so let's say someone later tries to access this resource B, it will the request cache handler will go and look it in the cache. It will say, yes, there is something in the cache for object B, and it will try to load this cache file in the heap. How it's going to be done? Well, it's going to read first the length, and it will use that to reserve a buffer in the heap. And then it's going to write the entire request looking for null bytes. Okay, so it will write the entire response in this place. However, as you saw, the response is actually 106 bytes, and this is 95 bytes. So what's going to be happening is that there will be a buffer overflow in the heap, which will be tampering something else in the heap. And what's also stored in the heap are different structures that include, for example, the pointers to the other handlers. So later, this handler will be used for example, for another request when the Java handler is called. Okay, we can modify any handler actually. So if we are able to override this handler pointer, then we can modify the way that this structure is going to behave, and when this handler is called, instead of calling the actual handler, we can say, okay, call any position in memory. So we will be able to modify the instruction pointer and therefore to modify the behavior of the binary. Now, before we say that we have remote command execution, we need to note that it's not quite easy. We need to modify the response at the correct time. This is actually something we can do with a lot of attempts. Okay, so we can try to send to cause this tampering just at that specific moment, as I said, just after the request is being handled by the cache handler. We also need to hit the specific heap buffer, so this specific structure, and the specific position. If not, we are going to crash the ICM. That is what we are going to see a lot of times. We also need to defeat memory address randomization. That is quite complex. We will probably need another vulnerability. And finally, we will need to create a rope gadget. That's not really that hard. It's probably the least of the problems. But the most important one is probably defeating or knowing the layout of the memory so that we can actually create this rope gadget. Okay, so these vulnerabilities were stated to be CVSS 10 for the first vulnerability explained. The second one is an 8.1. We were not really sure why, because the attack complexity is high. However, the scope should be changed. Of course, if the first one was changed, then this one is even worse, but that is what SAP stated. And the solution these vulnerabilities affect all SAP products. This is the first time that a single vulnerability was affecting all the products in SAP, and more than 20,000 systems were exposed in the internet facing these vulnerabilities. So SAP released a security node, 2 security nodes, a manual workaround, and we at Onapsis created a detection tool that was able to determine if you are vulnerable or not, and to specify in which kind of vulnerabilities you were vulnerable. And finally, some conclusions. So the first one is this entire research was being done on ICM. However, the same concepts can apply to different HTTP servers. For example, to Microsoft IIS, to some other specific servers that are working with internal memory and are communicating through different processes, which is quite common because HTTP servers do not contain the business logic in many cases. And it was really interesting to see that the reversing of these servers is quite similar in all cases, because we need to have the RFC in mind. So if we know that what the intent of the server is, then we know how to analyze it. There are similar functions and workflows in all these servers, and it was really useful to identify requests and responses, and we can do it in all kind of products using, for example, the logs, which give us a lot of information about the memory. Then it was interesting to escalate low-level vulnerabilities in HTTP servers. In most cases, when we find a buffer overflow or something that compromises the memory of an HTTP server, it's not that easy to exploit it. So we can use these techniques like HTTP Desynchronization, web cache poisoning, and some other high-level exploitation techniques to actually leverage these vulnerabilities. And finally, the code name for these vulnerabilities was ICMAD. This was addressed by the Cybersecurity Infrastructure Security Agency from the US and different certs in the world. It has a critical impact. There was a lot of SAP servers being compromised because of this. And so there was a big campaign from SAP to modify and update their servers. And again, this was exposed in more than 20,000 servers in the internet, so it was quite critical. And that's it. Questions?
Any questions?
Hey, thank you for the talk. Very interesting. You kind of cut it short. Were you able to exploit the memory corruption in the cache handler?
Sorry again?
Were you able to exploit the memory corruption in the cache handler in the end?
Why I try to exploit that?
Out of curiosity, you mentioned it.
Why I didn't? So
yeah,
we did exploit that. However, we had to combine another vulnerability which was not present by default in all products, which gave us information about the layout of the memory. So after that, it was quite easy. However, again, this is not quite a reliable exploit, because when we launch the attack, in many cases, we will see that the ICM crashed. So if I try to show you that, it will take like forever. It actually takes like an hour, even though crashing the ICM is not that bad, because there is a watchdog that will take it back over and over again. It will take some time to do that. So in real tests, we said that it's like 2 hours from remote command executions. You can have remote command execution, but it will take about 2 hours.
Okay, thank you.
Any other questions? Well then, thank you very much, Martin Doyhenard.
Thank you.